Hello class. So this is problem 8 from the second workbook. And I mean I'm not gonna exactly do problem 8, but a very similar problem, okay? And I mean 99% similar. So let's talk about a bacterium that divides every 5 minutes. So you have a bacterium right there, and every 5 minutes this thing will divide by binary fission, okay? Then another 5 minutes go by and you're gonna have this many bacteria and so on. Okay, so I'm gonna do three things. I'm gonna create a function or discover a function that describes or that models that describes the population of bacteria as a function of time. That's the first thing I'm gonna do. Function of the time. Okay, remember every 5 minutes, this is time 0 minutes, this is time 5 minutes, this is time 10 minutes. So at each of those times, I'm going to create a function that as input will take the time and as output will tell you the amount of bacteria that you're going to have. Second, I'm going to calculate the number of bacteria at let's say 30 minutes, half hour. And number 3, I'm gonna find at what time I have a population of 1 million bacteria or more. Okay, so we can write that in this way. I have a population greater than 1 million bacteria. So that's the three things I'm gonna find. Okay, so let's do it. So this thing is known as exponential growth for a reason, right? You're gonna make use of exponential functions to model the behavior of this type of system. So let's create a little table in order to represent the following. I'm gonna have time as my independent variable, and I'm gonna have n, which represents the number of bacteria at each time. So this is my independent variable, and this is my dependent variable. So we say that this dependent variable is a function of my independent variable, and I need to write this. So we know this. Now, what type of function describes this behavior? Let's find out. So at time 0, let's suppose we have only one bacterium. At time 5 minutes, we have 2. At time 10, we have 4, 15, we got 8, and so on. Okay, so first thing I can notice is this. All of these guys, all of these numbers, 1, 2, 4, 8, 16, 32, etc., are powers of 2. These numbers can be written as 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and so on. So I already have a glimpse that my function will be exponential. Okay, because the only thing that is changing in here, in these numbers, is the exponent. And when the thing that changes or that varies is your exponent, you're talking about an exponential function. Now, what's going to be that function? Is it going to be this, like f of t equals 2 to the t? Is it going to be this function? Clearly not, right? Because if I write this function, I would be saying that the population of bacteria at 0 minutes is 2 to the 0, which is 1. And in this case, it checks, okay? At time 0, I have 1 bacterium. So for this particular time, it checks. The problem comes when I try to calculate the number of bacteria at 1 minute. That would be 2 to the 1, which would be 2, okay? And that would be correct, okay? Why? Because at time 1 minute, I still do not get 2 bacteria, You see what I mean? At time 5 minutes is when I get 2 bacteria. You see what I mean? Not at time 1 minute, at time 5. So it doesn't check. So I know for a fact that this is not my function. It's not like this. So what is the trick? The trick is doing this, guys. The trick is, and this is also another trick very common in mathematics. Let me erase all of these numbers. The trick is thinking of your times 0, 5, 10, 15, etc. as having a relationship to 0, 1, 2, 3, and so on. Okay? Kind of like do some sort of match. This is your first time, okay? This is your second time, this is your third time, and so on. But multiplied by a factor of 5. You see? If this is my time 1, then 1 times 5 is 5. If this is my time 2, then 2 times 5 is 10. So basically we can think of this as changing by a unit, but by a factor of 5. I don't know if I'm confusing you. It's difficult I find it difficult to express. So basically the function, now that I have this sort of vague idea, what I can do with the function is this. I can, since I'm multiplying my unitary time by a factor of 5 in order to get the real times, which are this, what I need to do here in the exponent is divide my time over 5, over that factor, okay? This will be my function, guys. This will be the function that gives me this number of bacteria for these times, okay? Let's check. F of 0 will be 2 to the 0, right? Which is be 1. So it checks. For time 1 minute, I get 1 bacteria, so it checks. Now, the function evaluated in 5 minutes. So let's go right straight to 5 minutes. The function evaluated in 5 minutes will be 2 to the 5 over 5, which is going to be equal to 2 to the 1, which is going to be equal to 2. So it does check, right? Because at 5 minutes, I do have 2 bacteria. You see? So this is the trick, guys. Dividing over your factor. If you consider all of these numbers to be changing by unit steps multiplied by a factor of 5, that's what you have to do in the exponential function. You have to divide your time in here over such factor. And just as a remark, what does this thing remind you of? Anything? Anybody? We are dividing the variable in my function, only the variable, by some factor. Does this mean like some sort of stretch? What type? Horizontal or vertical? It's horizontal, right? By a factor of 5. You see what I'm saying? Because that's what we're doing. If these were my initial values for the time, all I'm doing is stretching them by 5. I'm multiplying all those values by 5, so my factor is 5. I'm making a horizontal stretch by a factor of 5, and that's what's happening. See in here, you see. Try to understand what I said. I know that I may be failing in my explanation somewhat, but I think you can get a feeling of what I'm trying to say. So this is my function, guys. And number 1 checked. We're done. Okay, let's go to the other 2 things are very easy. So now that we have the function, which is the difficult part in any mathematical problem, you see, it's get the model. Get the model. The rest of the calculations are easy. Once we have the model, the rest is, a piece of cake. Number 2, calculate the number of bacteria at 30 minutes. Okay, I just have to use my function. I go like this. By the way, this was 1, this is 2. I evaluate the function in 30 minutes. So I'm gonna get 2 raised to the 30 over 5, which is gonna be 2 to the 6, which is going to be that's gonna be 64. Okay, 64. I think I'm doing something wrong. No, everything is fine. 64. Everything is fine. If you find a mistake, you tell me, okay? But I'm 99% sure this is correct. Okay, so number 2, done. And number 3, find at what time we have a population of bacteria greater or equal than 1 million. So again, I use my function. This is my function, f of t, which is the population of bacteria, is equal to 2 to the t over 5. Okay, and I need the population of bacteria, which is this, to be 1 million. So I substitute equals 2 to the t over 5. Now, please do not write these numbers in this way. Okay, or I mean, there's nothing wrong with this, but try to use scientific notation. That's why we invented scientific notation. So this is just 1 times 10 to the 6, or just 10 to the 6, right? It's the same. And now I only have to isolate t from this exponential function. What do? We go to the logarithmic equivalent representation. If 2 to this raised to this number is equal to this, that's because the equivalent logarithmic expression or equation should be this: logarithm base 2 of this number is equal to t over 5, right? This thing and this thing are completely equivalent, mathematically equivalent. Remember, the logarithm base 2 of some number is equal to another number when this raised to this gives me this, which is in fact what we have in there. Okay, and then you can solve for t. I'm not gonna do it, okay? You can do that on your own. We have done that before, and I don't wanna keep you entertained in this video. So that's it, guys. Problem finished.